Okay. All right, here we go. So the lesson that we are not doing today is one slightly different step in this whole process that I'm about to show you and remind you of. So the new thing that we will cover next class, I will kind of preview it a little bit today just so you have a chance to let it sink in. But it's only when the process is going to stay exactly the same, but only when we're dealing with a really small sample size. We have to do a slightly different version of things. So I don't know if you guys remember, but like even when we went from pennies to quarters, yes, everybody know what I'm talking about. When we went from pennies to quarters, I knew that that quarters graph was going to be a perfectly normal curve. I knew that going into it. But you guys couldn't actually see that because there were only, I don't know, 50 to 60 quarters in that graph. So you couldn't see like the gorgeous perfect normal curve. It was definitely more of a normal distribution than you could see with your pennies, but you couldn't see how beautiful it was going to be because we didn't have enough quarters making the graph. Does that make sense? So when you don't have quite enough data, they get a little disjointed and a little clunky like that. So instead of using the normal distribution, we have to use what's called a t-distribution. But all that changes is the fact that we're not using a z-score and we're not using the same page in the back of the book that has been marked since the beginning of time, this page A104. Instead, we'll be using page A105. And you just read the table slightly different. So the only thing that's changing is basically which of these two pages you're going to use, or instead of a normal CDF in your calculator, there's a T-CDF that you would use, okay? So that's our lesson for next time, essentially, but we'll go through and we'll do a problem next time so you can actually see it again beginning to end. But yeah, we're just looking at next time small sample sizes, which our example that we're going to do together today has a sample size or a number of draws that's 10,000. So nowhere on any one scale is 10,000 a small sample size. Okay, that cutoff is going to be actually the number 15 for us. So 10,000 is obviously way bigger, so we're going to proceed like normal. Good? Okay. All right, so question number 7 on the gold packet. I'm going to go a little bit slow, okay, just to kind of re-give you, reteach the lesson for anybody that missed, but also for anybody that has spring break brain. It's been a minute, okay? So I am going to take it step by step, break it down. Please stop me if you have questions. And yeah, here we go. So number 7 starts out with just saying a coin is tossed. And I know that for you, it's not going to be natural to see a coin is tossed and stop reading and go ahead and write your hypotheses. But really, in the whole scheme of things, that's what should be happening. You should find out that the process is that they are going to toss a coin, and you should immediately be able to draw or come up with your null hypothesis and alternative hypothesis. Okay, so we're going to start there. If we preview the rest of the question just a little bit, we find out that they tossed the coin 10,000 times, came up with 5,167 heads, and our question that we're trying to answer is the chance of heads equal to 50%? Does anybody know, like in the gambling world, what that is called? If we're testing a coin to see if we get exactly 50% heads, we're trying to see if the coin is a fair coin. You heard this before? Okay. Have you ever heard of a loaded dice or a loaded die? Same concept. So you can load a coin so that it has a higher tendency to land on heads or tails, whichever one you want. You can load a die so that it'll land on 6 more often, just by weighting it different. Okay, you can even like apply multiple clear coats of essentially like a nail polish to one side of the coin or to one side of a die, and it'll weight it so that it does what you want it to do if you're trying to cheat, which we would never do. So not an issue for us. Anyway, so essentially this question is about testing to see if a coin is a fair coin. So a null hypothesis, when we go through and we make a prediction about what might happen, the null hypothesis is always no change. There's nothing wrong. Everything is as it should be. Always. That's always the way the null hypothesis works. So in a question, if they're giving you data about how it used to be, so 20 years ago, they ran a study and this is what happened. That's your null hypothesis. Or somebody claims that this is true about the population. That's your null hypothesis. Whatever is the claim or something that used to be true, we're always assuming there's no change, there's no problem, and that is our hypothesis. The thing we're testing is going to show up in our alternative hypothesis, okay? So the H with the 0, if you guys remember, that's our null hypothesis. And because the null hypothesis is that there's no change, no issue, our hypothesis is what? What? Oh, who said something? It's 50%. That the percentage of heads when we toss this coin over and over and over again is going to be 50%, okay? So our hypothesis is that tossing it over and over and over again, we're going to end up with 50% heads. Been a while since I've recorded. I just wanted to make sure they could actually see my writing. Okay. All right. So what is our alternative then? Now, the thing that's tricky here, technically speaking, we talked about this when I gave you the original lesson, you don't come up with a hypothesis after you've performed the experiment. You come up with it beforehand. But we have to keep reading in the question to help us determine what our alternative hypothesis is in this particular test. They kind of give you the information in a weird order. They shouldn't be giving you the 5,167 in the first sentence. That should come later, really. Really, the question should start out with, is it a fair coin? But because of the way they worded it, if you read that very last question, well, there's two questions at the end. It says, is the chance of heads equal to 50%? So is it a fair coin? Or, read that last part. Are there too many heads for that? So they've kind of already, we call it data snooping. They've kind of already looked at what happened. And we are expected to formulate our alternative hypothesis based on that question. So we always have three options. With our alternative hypothesis, we're still going to be talking about the percent of heads. And we always use the same number. The question is, what goes here? So we have three options. You ready? It could be a not equals to sign. It could be a greater than sign, or it could be a less than sign. If this question had been worded, we're going to toss a coin 10,000 times to see if it is a fair coin. If that's all they gave you, you would definitely choose the not equals to option. Agreed? Because we wouldn't know going in before we ever toss the coin. If we're trying to see if it's weighted, we wouldn't know which side it was weighted on. We wouldn't have any of that information. This particular question, though, at the very end, they said, are there too many heads for that? Yeah? So it's kind of like someone saw this coin in action beforehand, lost a bet or something based on this coin. Now they've brought into question the validity or the fairness of the coin, but already with a hunch that maybe it's showing too many heads. So instead of using the not equals to option, in this example, we're going to use what? If there are too many heads, we're going to use the greater than. Okay? Just because of the way the question was worded. So you're going to have to watch carefully for wording that clues you into one way or the other. Good? Okay. So in the actual question, the first thing it asks you to do is to formulate the null and alternative hypothesis in terms of a box model. I've written my null and my alternative hypothesis. I need a box. So tell me what goes in that box. So I would call this step 1. Now we're going to create a box. So that's going to be our step 2. Okay, London said there are exactly 2 tickets in this box. What are they? A 1 and a 0. Somebody else tell me what the 1 represents. The heads. A 1, when you draw a 1, that is symbolic of tossing the coin and seeing heads up. So the 0 must be tails. Okay, when you create a box model, it's important that I know how many tickets are in the box, what the tickets have on them, and what they represent. And then we also need to mention one other thing. Does anybody know what it is? Number of draws. How many times are we going to draw out of that box? Okay, so a couple of questions. First question, why are there not 5,167 ones in the box? Well, 5,167 ones, and then what would that be? 4,833 zeros. Why is my box not set up like that? Right? So just because I drew 10,000 tickets doesn't mean there's 10,000 tickets in the box. In fact, that's a little weird. For the number of tickets in the box to be the exact same size as the number of draws, that's a little like, oh, why did you draw them anyway? Why didn't you just look at the whole box? Right. Also, the 5,167 is a sample. What is the box? It's a population. Okay? Most important at this moment, you need to understand that that box has to be modeling what is happening in the null hypothesis. You have to understand that that box came before you ever saw the number 5,167. Yeah? It has to be 50-50 because that's what we said in the null hypothesis. Does it have to be 1, 1, and 1, 0? No, it could be 10 of each. It could be 700 of each. It doesn't matter. Okay? If we had billions of ones and the same number of zeros, then we could draw without replacement. But technically, when you think about tossing a coin, you are replacing, right? You toss it, you see a heads. You didn't take the heads off of the coin. You left it there, right? So drawing tickets with replacement, same concept as flipping a coin, but it doesn't really matter. In the scheme of things, it doesn't matter how many tickets are in this box, as long as there is exactly the same number of ones as there is zeros. So if you had already read 10,000 tosses and decide, maybe not super intelligently, to put 5,000 ones and 5,000 zeros in the box, okay. I'm not going to tell you that your box is wrong. You're just thinking about it a little off. We need it to not be set up like that. We need it to just be heads, tails, done. Okay? Then we draw 10,000 times out of the box. Because even if we had 5,000 of each, we would still have to draw with replacement. Yeah? Does that make sense to everybody? Okay. All right, moving on. So we have our hypotheses. We have our box created. Now, if you look on the actual question, part B says to find Z and P. I don't think we're quite ready for that yet, but if you're not sure, if you see that and you're like, how the heck do I get from there to Z? Look at your formulas page for me. What is the, remember we're on the back side of the formulas page for this unit. What does your formulas page say about Z? It will be, yeah, just 1 second. So we go to do the next step on our assignment and it says we need Z. We look at our formulas page and Z needs all of those things. Do we already have all of those things? We don't have all of those yet. So that maybe clues me into step 3. Step 3 should look very familiar. Yeah? Every single time in our last unit that you drew a box, I always would recommend that as soon as you have a box, you find an EV and an SE. Question: percent, sum, average, or count? Pick one. Now I've officially heard all 4. Okay. Which one is it? It's one of them. Yes and no. What's the other option? Both, actually. I told you there was only one right answer. There were 2 right answers. Well, sum and count are the same. So I guess there's 3 right answers. There's 1 wrong answer. Don't use average. They didn't talk about an average at all in this problem. You're not averaging heads. Okay, that's weird, right? When your ticket is 1s and 0s, or when your box is full of 1s and 0s, it's either a count or a percentage. Okay? In this case, what did we write very first? When we started this problem, our first step was to write the what? The null hypothesis. And what number did we use in our null hypothesis? Percent, 50%. So that tells me right here, I'm going to use percent. So how in the world can the option of count also be correct? You could have started the problem, instead of writing a coin is tossed, we could have written a coin is tossed 10,000 times. So then my null hypothesis could have been the number of heads will be 5,000. That is a count, right? You would use sum to add up all the tickets in the box, but that's a count. We're counting how many heads, okay? Then that would change everything from here on out. I'm going to use percentage because that's what we started with, but you will get the exact same answer if you go through this whole problem using count instead. Nope, doesn't matter. It's basically the same calculations no matter what. Yeah, don't mix them. Yeah, one or the other you have to decide up front. And generally what I do is this. This 50% that I wrote right here needs to also exist in the box. Do you see the 50% in the box? I never wrote 50%, but you know it's 50%, right? Okay, that 50% should also exist here. Everything all cute and matchy-matchy. Yeah, just keep using it. So if we had instead used the 5,000, okay, then there would be something to do with 5,000 down here and something to do with 5,000 over here. Good? Okay, here we go. All right, so expected value percent. these expected values should come very easy to you. You don't need a formula. Because the expected value is given to you when you're trying to come up with your null hypothesis, you just transfer it over. It's just that. No calculation or fancy formula needed. Good? SE percent. What does it say? You guys have seen this before, yeah? Okay, so I have two options for you. You need to tell me which one I should use. I forgot what this was. 4833. Everybody think about it for a second, because not very long from now, you're going to have to decide this on your own. And written as decimals or written as fractions doesn't matter to anybody, right? We're all okay with that? So it could be like 50 out of 100, 50 out of 100, or 5,167 out of 10,000, 4,833 out of 10,000. Doesn't matter which way I write it, but the question is, should I be using 50-50 or 51-67, 48-33? I'm still hearing both. Yeah. Yeah. EV, SE from the box. Always. What is our box? Our box is 50-50. Sorry about it. Yeah. EV and SE from the box. Okay, we already made our box match our null hypothesis and our expected value. So we use that same number again here. Not this. Right now. Well, in like one more second. Okay, so we expect 50% heads. We expect 50% heads, which means our box is 50-50, which means the percentage of ones in the box is 50%. The percentage of zeros in the box is 50%. Finish SE for me. This is only SD, correct? Okay, finish SE percent for me. What do I still need here? Okay, do that and tell me what number you get. Tell me if it causes any heartache, confusion, sadness. If you are already having heartache, confusion, and sadness, you should have stopped me and asked a question a while ago. Just kidding. Okay. I know, rough, huh? Why did we have to come back from spring break? Wasn't my idea. Okay, what did you get? 0.005. That's what your calculator says. Is that the number I write on the board right now? Why? What's wrong with it? Not a percent until I move the decimal twice. It's still a decimal within the percent, which for some reason causes people to be a little sad, okay? But it's still only 0.5%. So it's only 0.5%. So before we move on to when do we actually use the number that they gave us, what is this number? Give or take on what? The percentage of heads when flipping the coin 10,000 times. Do you understand that this number is impacted by that insane number of coin tosses? Yeah. Does it make sense to you that this number is much larger if we only toss the coin 10 times? Yeah. Okay. Because the error, the give or take, is a lot higher, right? It's when we toss a coin 10 times, is anybody shocked when we only get 30% heads? No, because the error is a lot higher. But when you do it over and over and over and over and over again, it gets closer to 50%, which means our error is getting smaller. So we're saying right now that when we toss a coin this many times, we're expecting somewhere between 49.5% to 50.5% of our tosses will be heads. That's pretty specific, right? But only because the sample size is so large. Yeah? Okay. Now, there was one thing in our Z formula that we haven't talked about yet. What is it? So Z says observed minus expected. Now, remember, this is just, sometimes we call it benchmark, but you guys have learned expected over and over and over again. So that's a either word. It's not like a multiplication thing going on in that formula, okay? So we use the word expected, we use the word, expected, sorry. Instead of benchmark, that's why it's on your formulas page. What part have we not discussed yet? Observed. What is it? Do you see this right here? We wrote our expected value in percentage form. We wrote our SE in percentage form. Does it make any sense at all now to talk about our observed value in count form? No. So what do we need to do? There we go. 5,167 heads divided by 10,000 tosses. Turn it into a percent. 67%. Got it? That makes more sense, right? It's hard to compare 50% to the number 5,167. Yeah? So we change it so that they're all the same. Nope. No, so if we were just using count, this would be 5,000. This would be not divided by 10,000, so I can't remember. Is it? No, because if it was just a count, yeah, so 5,000, that makes sense. So 5,000 heads, give or take 50 heads, and then we ended up getting 5,167 heads.
Okay, so I'll just follow like that.
Yeah. Yep. Good? You feel okay about that? Okay. So that was step 3 of our process, but we haven't actually done what it asked for in part B of the question. It asked for Z. That's next. Okay. We call this the test statistic. A statistic, meaning it's a number coming from the sample. Yes? Good? Okay, and we're running, it's called a hypothesis test. So this is our test statistic. This is the number that determines how far away our observed value is from our expected value. Z equals what? Observed. What is it? 51.67 minus expected divided by SE, which is 0.5. 3.34. Now, pause for a moment and ask yourself, does 3.34 seem okay as a Z-score? Does it seem okay? It's not great. It's not ideal, but is it okay? We get 99.7% of our data within 3. Can we go outside of 3? We can. Here's why I bring it up. Because I will have people that will not move this decimal. This guy right here. If you did this again, but instead of dividing by 0.5, what if you had divided by 0.005, which is what your calculator said? Do it. Do 1.67 divided by 0.005. Is that okay as a z-score? No. A little beyond 3 every once in a while is not the end of the world. But a z-score of 334 better warn you, better throw up red caution flags all over the place. That is not something that should be happening. Okay? Even anything beyond 3 and a little is just not okay. Something's wrong. I think there might be a question, depending on how you round, that turns out to give you a z-score of 4. If it's still in the table in the back of the book, then it's okay. It's tiny. It's basically 0. But that's how these tests work. We're looking for things that are highly unlikely. So our percentages are going to be really low, which is why sometimes we get beyond the 3. Okay, so don't panic if you're outside of 3. Panic if you're outside of 5. Okay?
So basically you're saying that you don't think it's a weighted coin because it's like less than 5.
Hold on. We're almost there. Takes forever. I know. Sorry, because I talk a lot. Okay, so we have Z. What else are we supposed to find in that step? P. How do we, does anybody remember what P is even? It does have something to do with probability. Yes, it does. So P stands for probability, but actually P is what we call the observed significance level. Okay, so take this off for just a second. Significance, what does that mean? Like, is it a big deal or no? That's what P tells us. Is this a big deal? Is 5,167 unreasonable? Is what this will tell us. Yeah? Just like, is 2 a big deal? Well, if you're talking about M&Ms, no. But if you're talking about GPA, yeah, kind of. Right? So is the 167 extra heads from this coin toss, is it okay? Is it like within normal bounds, kind of? The reason there's an observed right here is because we had to use this observed value to get to this P value. So there is a question on your homework that says something to the effect of the observed significance level has or is impacted by the data. Yeah. Because we had to use the data, like the actual observed numbers, to get to Z, and use Z to get to P. So definitely yes. This number is impacted by what we actually saw in our data. Okay? All right, so how do we get it? 2 options. Normal CDF, back of the book. Okay? Normal CDF is going to feel pretty normal on this problem, but for one reason only. The one that we did when I gave you guys this lesson the first time, I don't know if you remember, but we used a not equal sign.
Bertie?
Yeah.
Hey, do you have Cole Marino in class?
I do.
Could you have him come and find out at the office? He's checking out.
I don't really want to go.
Okay, I will. If he can manage to get his butt out of his chair, he'll be there. Okay. So, I don't know if you guys remember this, but I'm going to remind you right now. When your alternative hypothesis uses the not equal sign, that means you're testing both sides. You don't know, like let's say you assume the coin isn't fair, but you haven't you don't have any inkling about which direction it's not fair. Does that make sense? In that situation, when you get to the point where you're considering a normal curve, you have to add this area and this area together to get your p-value. But if you use a greater than sign, then that means your observed value is probably higher than expected. And you only have to consider this area up here. I already have a hunch that it's greater than what was expected. So I only need to calculate this area. These extreme values that are higher are the only ones that matter to me. Okay? And then in this situation, obviously just that lower tail. These two pictures, you have so much experience using normal CDF. Agreed? We go low, we go high, we go middle, we go SD. Done. We got it. We've done it so many times. You have never done this on normal CDF before. Okay? And there isn't a way. There isn't a way to normal CDF and get both of these at the same time. So if you use your calculator on a curve like this, then you just do normal CDF for one of them and you double it to get your p-value. So in this situation, it's actually faster to just use the back of your book because the back of your book is already set up this way. In these situations, it's kind of sixes. It really is. It's not really any faster to use the back of your book or your calculator. Only because, so last time we saved ourselves tons of time and effort using normal CDF because not only did it just like spit out the answer and it's exact and we didn't have to round or anything, but also because we got to skip this step where we came up with our own z-score. These questions require you to say what the z-score was, so you already know where that mark is exactly. Normal CDF, you didn't have to do that up front, okay? But we have to. That's part of the questions. It will ask you for your actual z value, so you're already so close to just using the back of the book. So again, doesn't matter, okay? But it does leave a couple of options. So 3 options here, which seems intense. So the book. So we look for what number? We're going to find the area by looking up what number? 3.34. Okay, so remember it's on page A104 in the back of your book. I go to look for 3.34. There's a 3.30 and a 3.35. Which should I pick? 3.35. It's always just closer. Doesn't matter higher or lower, just closer. Okay, so 3.35 is the z that I found. The area that it gives me is 99.919. So we're looking at a z-score of 3.34, which hopefully you guys understand. That's clear the frick up here, yeah? I'm looking for this area. Is that 99.9% of the area of that curve? No, it's not. What is 99.9? It's the middle. Match this guy over here, and 99.919% is in the middle. Yeah? What math is required to get to just the area in that upper tail? 100 minus 99.919, cut it in half. Okay, that's option number 1. Are you ready for option number 2? Maybe. Option number 2, calculator, normal CDF. Pull out your calculator. Low. What's the low value? Anybody? I got a negative 999 as an option. What is the low? Do you know what I'm trying to find? I'm trying to find that. So do you understand why the low could be, remember there's three options, so this is just their second option. The low could be the number 3.34. Does everybody understand where that came from? If I look at this z-score is at 3.34. Okay, so I could do that. In that case, what is the high? Just your 9s is fine. Here's where everybody crashes and burns. It's 0 and 1. Why? Does 3.34 have anything to do with the 10,000 tosses? Or the 5,000 expected? Or the 50%? No, 3.34 is what we call a standardized value. It's 3.34 SEs above expected. Okay? But it's on a standard normal curve. So when I type in 3.34, I'm thinking about the normal curve that's centered at 0, and my gaps are 1. 3.34 and up is that area up there, but with this center and this size of an SD. Yeah, you follow? 0, 1. Okay, type that in for me. I want you to see something. I think all of your calculators are going to give you, I think they will all do the same thing. Okay, we said that the answer was 0.04 based on our book. And I have so many students that look at this calculator and go, oh, 4.18. Is that what that says? No, but you don't have a lot of practice with these weird numbers. So this says 4.189, then some other numbers, but then there's this. What the frick is that? It's like a scientific notation thing. We got to move our decimal. How many times in which direction? 4 to the left. So if I move that 4 to the left, that gives me 0.0004189. What do I always do after normal CDF? Move it to the right twice to make it an actual percentage. Your book is giving you numbers already in percentage form. Your calculator gives them to you in decimal format. So then I move it twice and I get 0.04189. Does that look a little bit closer to that? But do you understand how bad it would be if you told me that your answer was 4.189? Okay, good. Yeah? Okay, so watch out if you're using your calculator. Why did I say there's 3 options then? Does anybody have any idea what the other option could be? Still normal CDF. What would be my low? If it's not a normal curve, if it hasn't been standardized yet, what number is in the middle? 50. Right? And what's my low? Where am I cutting this off? It should look just like this picture, just with different numbers. What's this number right here? 51.67. How big are my spaces? Oh. So 51.67 is actually up there. Just kidding. They are 0.5. So this is 50.5. This is 51, 51.5, 56. Do you see how 51.67 and 3.34 are the same spot? So if my low is 51.67, what's my high? Still the 9s. Middle, 50. Yeah? Then what? What's the last number? 0.5. If it gives you a different number, then we should be sad because it should be the same. Good? Okay. You feel good about those 3 interchangeable options? Okay, yes.
You still have to change it to a percent when you plug in percent. Like at the very end, you still have to move the decimal places.
Your calculator, so what your calculator spits out in that moment is area under the curve. So it views this curve as 1. The whole number 1, as opposed to 100%. So it's not 100% of area under here, it's 1 under here. So this is a decimal that needs to be converted to a percent. Good question. Okay, we good about all that? We feel okay about all that? Yes? Are we done? Class is almost over, but no, we're not done. Hey, I'm just kidding. We have 20 minutes left to do some more math. All we've done so far is part B. I need a conclusion. How do I get from, oh, did I even finish part B? I just didn't label it. So step 5, I said we're looking for the observed significance level. What is it? This guy. Whichever one, depending on which form of calculation you used. Okay, so this or this, that is our p-value. What the frick is a p-value? I named it for you. Observed significance level. So step 5, nope, 6. Is to answer this question. Yes, it's never, you're never for something. You're never pro something. You're always against it. You're always trying to find evidence against it. So is it significant? Is it highly significant? And then step 7, technically, I guess, I don't know, come to some sort of conclusion.
Is the p-value in percent?
It's percents, yeah. So this is 0.04%. And we'll talk about exactly what that number means. Like, what is 0.04? I don't know. But I want you to answer this. Do you remember talking about 1% and 5% last time? So is it significant? The answer is yes, because 0.04 is less than 5. Is it highly significant? Yes, because 0.04% is less than what? What's the cutoff for highly significant? 1. So it is highly significant. Okay. What does that mean?
So it doesn't, not, we didn't fail to conclude it's small. It's like that. If the hypothesis were true, then the only way that we would get the alternate hypothesis or something different than would be
so close. So close. Oh my gosh. It kills me how close you are. So this percentage, 0.04%. Here's how it works. Ready? Are you ready for all these words? If the coin is fair, okay, and that's my friendly way of saying that the null hypothesis is true. So if the null hypothesis is true, if this coin really does give heads 50% of the time, there is only a 0.04% chance of getting 5,167 heads or more out of those 10,000 tosses. Yeah, let that sink in for just a second. This p-value tells you how likely your observed is if your null is true. Yeah? So p-value is a percentage. That's the probability, so 0.04% chance that this can happen if this is true. That seems like, When I see 5,167 compared to 5,000, I'm like, that doesn't seem like that much. But when we're talking about tossing a fair coin, after 10,000 tosses, the number should have been significantly closer to 5,000 than 5,167. So what did we just find? Evidence for the null hypothesis or evidence against the null hypothesis? Against. If it is lower than 5%, it is significant, and as a result, we reject the null hypothesis.
Wait, can you say that thing you said again? One more time. So if the coin is fair, only 0.4% chance of hitting 5,000. I just need to do it one more time.
So if the coin is fair, so if our null hypothesis is correct, there is only a 0.04% chance that we would get this percentage of heads. Yeah? So we reject the null. We are essentially saying, what? Put it into nice, pretty words for me. Yeah. The coin is not fair. It's weighted. There's something wrong with the coin. Because this, a 0.04% chance of something happening, not going to happen, and it just did. Yeah, we're saying it has this chance of happening, but it did happen. We saw it with our own eyes that there were 5,167 heads. It did happen. With only this much of a chance of happening, it did happen. Which tells us that, yeah, we saw this, so this can't be right. There's no way. You see how that works? Does that mean, wording here, so critical. Does that mean there is a 0.04% chance that the coin is fair? No. It is never pro the null hypothesis or pro even the alternative hypothesis. You're never saying there's this much of a chance that those are true. We're saying if that null is true, there's a 0.04% chance that this could happen, that observed value could happen. Good? You feel okay about it? You sure? Okay.
I get it. I just like I feel like so you have to like it's almost like making predictions because you have to do the highly significant and you have to reject it and you have to know
what it means. I know. So really, it's not very often that you need all three of those things. Okay? So right here, we can say it is highly significant. We reject the null. Our third conclusion is generally just wording the question, like answering the actual question. The actual question here was not, do you reject the null hypothesis? What was the question? Well, but read the actual question before we start, before part C. The actual question says, is the chance of heads equal to 50%, or are there too many heads for that? So we say the chance of heads is most likely not 50%. There were too many what? Heads. Then we've really answered the question. Yeah? Okay. You should always finish with a tie back to your hypotheses. That is a really well-written answer if this ties back to the original null hypothesis, the wording. Yeah, it's a mess, but go for it.